Good evening and welcome to Tinkering with Edkelar. Modern digital multimeters are accurate, reliable and easy to use. But what would a RetroTech workshop be without some old-school metering devices? I was looking for something that could measure inductance, usually called an RLC meter. A quick search on eBay yielded this nifty gadget from the mid-1960s, an ESI, Electro Scientific Industries, Model 250DE Universal Impedance Bridge. Interestingly, the brand is still around, although they no longer make those devices. This one here was advertised as not quite working, since one of the knobs was stuck. When it arrived, it was quite well preserved with only minor issues, a bit dusty, the BNC connector tarnished, the DQ knob was indeed binding up after a few degrees of movement, and the detector gain knob, which was rather, crunchy. That might need extra good cleaning, but everything else seemed pretty much spot on. The manual says that the device is powered by 4 D-cell batteries, yet the backside has a power socket. I was afraid that I had the wrong manual, but after opening the battery compartment, it quickly became clear. The OEM provided a rechargeable alternative to batteries. This replacement cover contains a transformer, rectifier, resistor, and a very much degraded NiCad battery. Brrr. Now, how to open this thing? There is only one visible screw on the back. And indeed, this is the only one holding the unit together. The style is similar to tube equipment, with the outer shell just draped around the front panel and chassis. The tight seal of the case also prevented any dust ingress. I must say, I never had a device on my desk that was this clean on the inside before. Wow, shiny! Still, the outside of the front panel and all the connectors required some good cleaning. I decided to remove all the parts from the chassis and, besides the usual recapping, give everything a good clean and a bit of fresh grease for the moving parts. There is a shiny golden can deep in the guts of the device. Looks almost like a can of tuna. Tuna. It has a trimmer and fixed capacitor parallel to it and only 2 pins. Weird. That style of can usually contains a quartz crystal and a heater, but that would require at least 4 leads. After following the wires and comparing it to the schematic, I found out this is a 100 nanofarad reference capacitor. They don't mess around with that. All the precision resistors are wire wound and probably also well calibrated. This promises to be a neat toy. Desoldering the binding posts was quite an effort. They take lots of heat and the wires were wound on the posts before soldering. Yeah, slight force was required. The binding posts are gold plated, so no oxidation there. The potentiometer for the DQ control is a sight to behold. Precision wire wound potentiometers are common, yes, but this one is actually a 3-in-1 model. There are 3 different ranges that share a common wiper. How crazy is that? I would love to clean the instrument glass on the inside, but the case is bent over shut like a tin can, and since it's working just fine, I'd rather not mess it up just for a tiny bit of dust. The LRC measurement dials are a set of precision resistors that actually dial in the ohms that you can read on the front. If you set the dials to 3, 1, 25, the combination yields exactly 3125 ohms. According to the manual, ESI had a trademark on that called Decastat. The front panel got a good clean with a magic eraser, while the buttons all get dipped and brushed to get the grime out of the nooks and crannies. The BNC connector was a different story. It seems that the surface is silver because by now it's almost black. Took a bit of polishing to get that shiny again. The detector gain potentiometer comes with the main switch, both of which were oxidized. Going in deep. Lots of carbon dust. Eventually I might need to replace that potentiometer, but for now it seems to work just fine. The device used a style of capacitor that I've never seen before. Also, a bit of asking around in electronics groups didn't come up with a clear answer either. It seems that these might be early tantalum caps, polarized but a solid plastic case. I found some matching tantalums for only $65 a piece. Yikes! I'd better replace them with normal electrolytics and a close value. They all say 20%, so the exact value doesn't seem very critical. Seeing that the transformer is for 110 volts, the charging circuit, if you want to call it that, is for NiCad cells, and I don't really mind batteries, I'm going to remove the charging parts and just slap on the cover plate on the batteries. The battery holder only has one clamp on either side, but needs 4 cells. I decided to make a tube, like the one depicted in the manual. I tried various conduits and pipes, but nothing was close enough. To make the required shape, I wrapped the batteries with some thin foam, followed by sticky foil. That turned out to be not quite stable enough, so I added a layer of duct tape. With some pull straps on the outer edge, I should also be able to remove the batteries easy enough and without any tools. The outer case was looking okay, but with the front panel getting an almost new look, I decided to add a fresh coat of paint to the case as well. Again, not quite the right shade of paint, but close enough for me. I taped off the carry handle and removed the battery holder so I could spray the full case. Reassembly time! First and foremost, the front panel needs to go back in. I don't like the components flapping around and tugging on the soldering joints. Some of these screws had odd lengths. I had to swap a few over when I discovered that they were slightly off. Also, the DQ potentiometer shaft apparently has an in and an out side to it. Humph! Okay, now the knob will fit. It took a bit of careful nudging to get the wiper aligned with the dial, but it works surprisingly accurate. One of the three wipers needed a bit of bending to make contact all the way across, because the other two kept lifting it up. And before I put it back into the case, I powered it up with my bench supply and did a few test measurements, starting with the battery check. Okay, seems to work now. Here I might need to call in for a quick timeout. Not everybody out there is familiar with a bridge circuit to measure impedance. The basic idea is to arrange an unknown impedance in combination with known ones and a variable one. Put the voltage across the circuit in one way and check if there is a voltage difference in the other way. If there is none, i.e. 0 volts, the variable and known impedances allow calculation for the unknown one. So we measure across here and twiddle here and here until we reach 0 volts. Note that the two impedances here are what gives the range multiplier and the DQ value for the inductors and capacitors. Once the circuit reaches an equilibrium, you can read all the values from the dials, multiply them by the range selection, and have the result. The basic circuit is known as a Wheatstone bridge, or since this one also measures inductance and capacity, a Wien bridge. While this method is extremely slow, it is also extremely accurate. This is not how you want to measure a random pile of resistors. This is what you use when you really want to know. Now, back to the measurements. Resistance measurements. The DC detector mode will show plus minus on the scale, so you can always know if your current selection is too low or too high, which makes adjustments easy enough. We start off by assuming a mid-range value. Then we put the gain control low and select a range that provides the least deflection. Turn up the gain and twiddle with the decade until we homed in on the actual value. Ta-da! Capacity. This one requires AC to work. For DC, the cap should be an open circuit. The device comes with a built-in 1 kHz generator detection circuit. It does support external signals too, between 10 Hz and 10 kHz, but that also requires an external detector. The built-in meter only works with the 1 kHz sine wave that the instrument creates by itself. Should be good enough for most measurements anyway. The downside of AC measurement is the detector only goes one way. There is no plus or minus in this mode, so the twiddling has to be done up and down to find the local minimum. Also, we need to adjust DQ as well as LRC. Inductance. Almost the same as with capacity, but there's a series and parallel mode available for higher and lower ranges. Another quick side note. The D and Q values are inverse to each other. 1 over D equals Q and vice versa. But it's more common to use D for capacitors and Q for inductors. The D value allows calculating the ESR or equivalent series resistor for a specific frequency. Ideally, it would be 0 or very close to it. The formula is R ESR equals D divided by 2 times pi times frequency times capacity. So for a 100 nanofarad capacitor at 1 kHz and a D value of 0.1, that would give us 159 ohms. Whereas the same D for a 100 microfarad capacitor would only yield 159 milliohms. The math is complex, literally. Bottom line, the lower the D factor is, the better. Absolute values depend on frequency and capacity, so saying that 0.1 is good or bad without a frame of reference is pretty much useless. And that's it for this episode. I hope you enjoyed this little project as much as I did, and maybe even learned a bit about bridge circuits. I'll drop in some links in the description. See you next time! A quick glance at eBay showed that this needle get. A quick search at eBay yielded this needle. A quick search on eBay yielded this needle. A quick search on eBay yielded this nifty gadget from the mid-1960s. Yes! Finally!